Hello everyone. Today we are going to continue our chemical equilibrium and actually finish up this unit with talk about Le Chatelier's principle. Basically what Le Chatelier's principle says, if we disturb an equilibrium, the reaction will shift to undo the disturbance. Okay, but what does that mean? So first of all, we have to look at this. With Le Chatelier, we're starting with the system at equilibrium. Right? And remember, when we're at equilibrium, the concentrations of everything in the system will be constant. Okay? And it's going to stay that way unless we make some sort of change. We call these changes stresses. Okay? The three stresses we're going to look at with the Le Chatelier's principle are concentration, pressure, and temperature. So a stress is something we change from the outside sources. Okay? So if we look at this reaction, we may have a container that has some mixture of N2H2 and NH3. It's at equilibrium. The concentrations aren't going to change. But let's say we come along and do something. So we have to inject, say, more N2 into the system, or remove some NH3, or maybe simply we heat up the container. Or let's say we put all of those gases into a different size container. Okay. So what's going to happen? Well, the system can only respond in one of three ways, right? It's just a chemical reaction. There's only three things that can happen. Okay. One is, right, we consume some of the reactants. So some N2 reacts with H2, forming more NH3. Okay. When this happens, we call this shifting right. Right. Simply the fact that, let's just pull up a highlighter here, or laser pointer. Simply the fact that we're consuming some of this, making more of the product on the right side, we call that shifting right. Okay. Again, this really is just shorthand for saying the amount of NH3 is going to go up and the amount of N2 and H2 is going to go down. Okay. The other response the reaction can do, or that can happen with a chemical reaction, is we can consume some of the NH3 and make more N2 and H2. Again, we're consuming the right hand side, making more of the reactants on the left, so we call this shift left. So the terminology would be our equilibrium shifts right or our equilibrium shifts left. The third thing, which really actually isn't a thing, is do nothing. Right? Sometimes there's no way for the reaction to shift to respond to the stress, and in that case, it's not going to look like anything happened from the reaction standpoint, meaning the concentrations of everything will stay the same. The other thing we want to be sure that we're looking at when we're talking about Le Chatelier's principle is that we're always talking about a system that's already reached equilibrium. So we say, okay, we come across a system that's already at equilibrium. So we've run the reaction, whatever mixture, we're now at that equilibrium point. This stress, again, a change in something, concentration, temperature, etc., and we're going to compare that initial equilibrium or old equilibrium to the new equilibrium. Okay? So when we look at this, we're going to compare how old equilibrium concentrations or amounts compared to our new equilibrium concentrations or amounts. Basically, we're just going to answer the question, do the concentrations go up, down, or remain the same for anything in that reaction, or everything? And this is just a graph to kind of illustrate that point. So we see at the beginning here, all the concentrations are constant. Okay. We reach this 4-minute point, something has happened. We're going to look later, we'll be able to identify what actually happened here, but we're not going to do that at this point. But we see something happen, the concentrations are changing, until again, right about 8 minutes, they've reached equilibrium because we see everything leveling out or flattening out or plateauing. Then again at 10 minutes here we see another stress, right? Something happened. You might be able to guess this one. You can see some CO or carbon monoxide was removed. We see the sudden drop. Again, the system responds. The concentrations of everything will change once again until they level out and reach equilibrium. Again, another stress here at 14 minutes. We've removed Cl2, we remove CO, and remove COCl2. Or in other words, we removed everything. Again, what's left is going to respond in such a way that it's going to reach equilibrium. Okay? So while this is a little bit complicated graph, and because we see like 4 different stresses happening here, or at least 3 different stresses, it's just illustrating the point that we're talking about. We're at equilibrium, something happens like here, because we see these starting to change. Again, we reached equilibrium, something happened. Again, these something happenings are what we call a stress. Let's take a look at these stresses that we've been talking about. Our first one is looking at changing reactant or product concentrations. Okay. We can do that by adding something, so N2H2 NH3, simply injecting that gas into the system, or removing one of the gases. A little harder process, but still we can separate out a gas and remove it. The point being that we are doing this externally, meaning we are physically putting some N2 in or removing some H2 or something along those lines. So let's look at what happens when we have one of these stresses. So as we mentioned a few moments ago, right, we're always looking at an initial equilibrium and what changes. So here we see that we have H2, NH3, and N2 at some concentrations. We can read it, it's 3 for H2 and so forth. It doesn't really matter for us, we just want to look at how the system responds. Okay? So we're at equilibrium, it will stay this way forever until something happens. Well, let's look at one example of happening. Okay? So here we can see that this blue line jumps up at this point, okay? Which means from a graph standpoint, it means instantaneously the concentration jumped up. That tells us that we've added N2. So the stress we're having here is too much N2. Okay, so our stress, let's just write that out. Our stress equals too much N2. Okay. Well, again, our reaction can only respond in one of 3 ways. Okay, one of those is do nothing. So let's look at the other 2. Okay, the reaction can either consume some of the reactants and make more products, or in other words, shift right, or it could consume some of the products and make more reactants, or in other words, shift left. So if there is too much N2, how should the system respond? If you said consume that and make more product, you are correct. This is going to shift right. And if we open up that graph, all of our ink is going to disappear, but we see that the N2 is going to go down, the H2 is going to go down, so these reactants went down, and the NH3 increased. Okay. So since N2 is the one we actually changed, we're going to kind of ignore that in the sense of comparing old and new equilibrium. But when we look at H2, at old equilibrium it was 3, now it is something lower, as we would expect. We shifted right, this went down, or we can put an arrow. Our shift is to the right, this went up. Okay, so we could say this in several different ways. And again, remember, we've established new equilibrium. We're comparing this line with this line. Okay, so H2 went down, and then H3 went up, or we can just shorthand say equilibrium shifted right. if we look at this graph, we can tell that H2 was removed at this point. It also tells us that down here. And so if we remove some of this, I'll just put a down arrow here. I'm going to circle it because that is what we changed. And we want to look at how the other two respond. Well, our stress now is less H2 or not enough H2. How are we going to make more H2? Well, we're going to shift this to the left. So our equilibrium shifts left. We could also say that that has to go down and N2 has to go up. The shift left and these going up and down have to be consistent, meaning every time we say it shifts left, it's just another way of saying products go down, reactants go up. Okay, so let's just look at each of these scenarios one by one. All right, so if we add N2, okay, again, I'm going to circle the thing we changed because we really want to isolate the other ones. So our stress is too much N2. As we said, that's going to go down. This is going to go up. Another way to say that is equilibrium is shifted right. If we increase H2, what should happen? Okay. Well, again, the stress is too much of something on the product or reactant side, sorry. So we should shift right. Again, shift right means that goes up. Any of the other reactants goes down. Okay. Likewise, we could add NH3. Okay. Again, circling it because that's what we are changing. So it's going to shift left, which means these are going to go up. Okay. So notice how when we add something, we're always shifting away from the side that we've added to. So if we add something on the reactant side, we shift right or shift to products. If we add something on the product side, we shift left or towards the reactants. Now if we remove, what do you think is going to happen? Again, the stress is not enough N2, so we need to make more. That's going to shift left, which means that's going to go down, and this is going to go up. Again, these up and downs are compared to our old equilibrium. So we had some amount of H2 before we removed the N2. Now if we look at the concentration when we reach new equilibrium, that will be higher than it was, and H3 will be lower. Okay. If we remove H2, again, since it's still on the reactant side, we expect the same thing to happen. Going to shift left, and shifting left simply means this goes down. On the product side, on the reactant side, it goes up. And if we remove NH3, okay, we're going to shift to the right towards that, meaning the N2 and H2 will go down. Okay. So again, notice when we remove something like here, we're going to shift towards that. We're trying to put back what was removed, right? So that stress is, we've removed some, the system says, oh no, not enough N2, let's make some more. The only way it can make more is consuming some NH3 and producing H2 and N2, and that trend continues. So when we add something, it shifts away from it. When we remove something, it shifts towards it. The next stress we're going to look at is really the change in pressure. Okay. We change pressure by changing volume. Okay. We know from our gas laws that if we decrease the volume of our container, the total pressure will increase. And when we're looking at Le Chatelier's principle, we want to eliminate other sources of stress, meaning when we talk about lowering the volume, you might think, well, won't that change the temperature also? We're going to assume that we keep everything else constant and that it's only the pressure that is going to change. Okay. So, if the pressure is increased, the system has to respond. Remember, there's only two ways, well, three by doing nothing, but two other ways that the system can respond. If we come down the reaction, it can either shift to the right, making more product and less reactant, or shift left, making more reactant and less product. So if we increase pressure, we want to decrease the amount of gas in the container. You might be saying, well, all those gases are there, we can't remove any. Okay, but if we look closer, we see that if we go to the right, we look at the coefficients of 1 and 4, which is saying for every 4 moles of gas that react, we produce 2 moles. So every time we make more NH3, we're actually reducing the number of gas molecules. So if we look at an increase in pressure, is going to favor or shift the reaction in the direction that has fewer moles of gas. In this scenario, we have 4 moles. We're just looking at the coefficients and only of the gases. These are all gases in our example. So we don't have to worry too much, but if one weren't, we wouldn't count that. So we have 3 plus 1, so 4 on the left and 2 on the right. We're going to shift in the direction that makes less moles of gas. So an increase of pressure is going to shift this right, again meaning N2 will go down, H2 will go down, and NH3 will go up. A decrease in pressure is going to do the opposite. So we want to make more gas because the stress is not enough pressure. We want to make more molecules of gas. In this scenario, we're going to shift left, or to the 4 moles versus the 2 moles. Okay. If these added up to be the same, so if it was 2 and 2, there could be no response. There's nothing the system can do. So that's the scenario where we see no change or no shift. This picture is just demonstrating how we change volume, since we're going back to gases that we started the semester out. We're changing the volume of container in a piston cylinder type of scenario. This is going to go down as these arrows show. We've now reduced the pressure. The system is going to respond by shifting to the side with less moles. Again, we're at 4 on the left, 2 on the right. And if you kind of count up these particles, you'll see, right, so this and this are equal. The pressure is going to have increased because we have the same molecules in a smaller space. The system responds. We have less molecules now, and the picture is a little hard to see because we can't see inside the whole container, but we're going to have reduced the pressure inside of there. Okay, I just want to put some numbers to this. So some people have troubles looking at this, but what we're kind of saying is, whether we're talking molecules or moles, right, we'll just use some numbers to make our lives easy. Okay, if we have, say, 8, oops, let's go back here and change this to pen. If we have like 8 moles of this gas and say 20 moles of this gas and 8 moles of this gas. Right. We could also say those are atmospheres because it could be depending upon the volume of the container. But if we add those up, that gives us 36 moles or whatever, right? And so we know as the reaction proceeds, if I consume, let's say 2 of this, right? I know this is a 1-to-3 ratio, so this is just stoichiometry. That if I lose 2 and 2, I have to, or not lose, but react 2 moles of that. I'm going to react 6 moles of that. And I'm also going to produce 4 moles of that, which means after that has reacted, right, I'm going to get 6, 14, and 12. And so we do the math here. We see that, yes, as the reaction proceeds to the right, because we're consuming reactants and making product, we see that the number of moles of gas is going to go down. Therefore, the pressure is going to go down. And these are just example numbers. We're not going to solve this mathematically. Just wanted to show how our last stress is change in temperature. Now, we have kind of done things a little out of order due to having to come out of school. So we didn't do our thermo unit first, and so we looked at a little bit of endo versus exothermic on the graphs in the first section of chapter 18. You'll see this delta H here. Well, let's just underline it. Okay. That really just is heat. It's a fancy term called enthalpy. We'll come back to that in our next unit. For us, what's really going to just matter for Le Chatelier's principle is that we can identify that if heat is on the left side, this is endothermic. Okay, we can treat it just as a reactant for Le Chatelier's principle, and exothermic is on the right side. Okay, so endothermic means we have to put it in. So reactants are things we put into a reaction. So say you're using the Bunsen burner, like the reaction we did decomposition, we added heat, right? Here, maybe it's just a combustion or burning reaction, we're going to give off heat. We'll get into these later, but endothermic has a positive delta H value. Delta H being negative is exothermic, but that's more of the thermo unit. Ours is just identifying that endothermic means the heat or energy is going to go on the reactant side, and exothermic, the heat or energy is going to go on the right hand side. So another thing is that we don't actually heat like the reactants only or heat the products only. So when we make the temperature hotter in a reaction, we're making it hotter for everything in there. So if we're at equilibrium with A, B, and C, and we're going to talk about the stress as adding heat, okay, we're not adding heat in this sense. We're going to add heat by just like heating the whole container. Okay. So again, we want to see what this stress is. So adding heat, we heat the container. Again, everything in there has to get hotter. Okay. So we want to shift away from the increase. Or in other words, just like we thought of heat being or like adding C, we would shift away from it. If we add energy or heat, we're going to shift left. And so this is what we changed. We made our system hotter. This is going to go down because we're shifting away from that thing we've added. These are going to go up. Okay. So in this reaction, we'd say this reaction is exothermic because the heat is on the right-hand side. We say forward reaction. By default, we talk about forward reaction, meaning the way it's written, reading left to right is the forward reaction, reading right to left is a reverse reaction. Okay, so if the forward reaction is endothermic and we make it hotter, and again, circling it, that's what we changed. We're going to shift away from that, just like if it were another reactant. And so these are going to go down. We're shifting away from the left, or we are shifting right, and so reactants go down, those go up. And again, if we decrease heat, make it colder, and we just take our container that has our A, B, and C, put it in the refrigerator or freezer, all of these are going to get colder. Our reaction is going to shift towards that, and so those will go up. That will go, whoops, that will go down, and that will go down. All right. So from the standpoint of actually just identifying what's going to happen, really it's not that much different from increasing or decreasing concentrations. We just have to recognize that this heat or energy can be on either side, and the terms endo or exo have some meaning. So once again, this is exo, meaning the forward direction, it gives off heat. Okay, this is endo in the forward direction, and so the heat is on the left-hand side. Okay. So our only really other thing that we need to talk about is the effects of K. We'll get to that in a second. This is just really saying what we had just talked about, that cooling favors the reverse reaction if the forward reaction is endothermic, meaning it's going to shift left. Okay. And shift right. Again, it's really just what we were saying on the previous slide. So we know that the only thing that changes K for a given reaction is temperature. Okay. So how does K change? Okay. Well, if the forward reaction is exothermic, so again, if we just write A plus B goes to C, if it's exothermic, we have our heat or energy on the right-hand side. So K, we're at 25C, might equal 2. Okay. Okay, at a higher temperature, say 50C, okay, if the forward reaction is exothermic, which this is, at a higher temperature, K should be lower. So maybe it's 0.53. Okay. These have a correlation, but not something we can easily just see. It doesn't have to do with the exact magnitude of the change. And so likewise, the opposite is going to be true if the forward reaction is endothermic. So we have A plus B plus our energy or heat. And you may see some values here. So this energy value is in usually kilojoules. So we have 115 kilojoules. Again, we don't necessarily know what all of that means exactly yet because we haven't done the thermo. But whether we write energy, heat, or some value with this J or KJ, so this forward reaction is endothermic. So again, if the K at 100 Kelvin, just to give different thing here, is 0.00, oops, we've lost 0.07, and K at 200 Kelvin. Okay, so since, as it says in this last statement, the forward reaction is endothermic, which it is, increasing temperature, K is going to increase, so it could increase to 0.190. All right. It might be a large jump between theirs. It could even be a much bigger jump. That doesn't really matter to us. We just want to recognize forward reaction exothermic, K will decrease with increasing temperature. Forward reaction endothermic, K will increase with increasing temperature. And now you know all there is to know about Le Chatelier's principle.
Have you seen Junior's grades?